Starting from question 41, determine whether the following pairs of structures are actually different compounds or simply resonance forms of the same compounds. The first thing you have to note is that there are hydrogens present which will inhibit the electron mobility. To have a resonance form, the electrons have to have, I like to think of it as a sink or an overflow where electrons can move through the atom. So A would not be the same compound. They would not be resonance forms. They would be different compounds entirely. B, we do see them to be the same compound because the electrons are allowed to move. They are close enough together to where the electrons can move between species, as illustrated here. In B, what's B? B is this species. The first thing I notice off the top is that there's a hydrogen here that's drawn out, and here there's a hydrogen, whereas this hydrogen becomes missing over here. I don't know where it went to, but what that screams to me immediately is that this would not be resonance structure. The hydrogen would have to shift over, and there are ways for that to happen, but for this case, no, that would not be a resonance structure, as better illustrated here, where we can in fact create this carbonyl double bond, but this hydrogen can't move from this carbon. Moving on to D, we see again the same problem. There are two hydrogens here that are not accounted for, whereas between these two species there's only one, which allows for some electron mobility, but this compound would not allow for resonance structure, as also illustrated here. Moving on to question D. Moving on to question E. They're weirdly associated in this textbook. But moving on to question E, we have this structure which looks like this. What jumps out to me? We see that there's an extra pair of electrons on this carbon. How did it get there? It looks like the oxygen was allowed to flow here, and then this double bond was able to move its pair of electrons over to this carbon, retaining an octet. Retaining an octet of electrons, which is possible. Therefore, E is in fact a resonance structure. F, this species, what immediately jumps out to me? Immediately jumps out to me. I see the electrons are in fact able to move from this double bond over to this nitrogen, and from this lone pair on this nitrogen over into form this double bond. Therefore, yes, it is indeed a resonance structure. Question G, I have illustrated here. We have a positive charge on the right carbon atom. This effectively creates a sink for electrons to flow into, allowing, as also illustrated here, allowing this double bond of electrons to transfer over here, leaving behind a positive charge on the leftmost carbon atom. So yes, this is a resonance structure. H, we see illustrated here, double bonded to oxygen and double bonded to carbon. This would not be a resonance structure. I could say more about this, but it would not be a resonance structure simply because the hydrogen cannot simply move from one end of the molecule to the other without some intermediate present, such as an entirely other compound allowing it to steal its hydrogen effectively. So no, this would not be a resonance structure. However, it is possible to see this in solution. Question I, we see similar problem. The hydrogen cannot just relocate from one end of the molecule to another. It wouldn't be a resonance structure. No, it wouldn't be. Moving on to J, we see what's the first thing we see? We see a sink here where electrons can flow into, and we see a electron-rich species here which can donate its electrons to fill the sink, to fill the void. So yes, you would see this as a resonance structure. Moving on to K, we see, what do we see? I see 2 electrons here on the nitrogen that can flow into this double bond. I see an electron sink. Oxygen likes extra electrons. It can uphold them. And as such, yes, this would in fact be a resonance structure. Because you simply need a place for the electrons to flow to, as shown here. In L, what do we see? I see an electron-rich species in this oxygen here. I see an electron-deficient species in this carbon here because of the oxygen pulling the electrons in the first place. And I see a double bond rich in electrons here. So I see the electrons moving from here to here, forming this intermediate, which is indeed the case as shown here. The electrons can move from this double bond over into this oxygen, and from this double bond over into this, to form this new double bond, which leaves behind a positive charge on the carbon where the double bond was once attached. So yes, it would be the same structure. It would be resonance form of that structure. So that's just the general answer key. If you'd like to copy the word for yourself, I mean, so be it. It's not a big deal. But that's what you want to look for when you're trying to draw resonance structures.